Section 3.7 on L'Hopital's rule, page 3, the final page. So there's two last types of indeterminate form that we need to discuss. The first of the two is called differences. If we ever have infinity minus infinity, it's of indeterminate form that can be rewritten to qualify for L'Hopital's rule, and then we can find a limit. So usually what you're going to want to do is factor if there's anything that needs to be factored, specifically writing the function in terms of sine and cosine if it's not already that form. And then you want to get down to a single fraction, which will usually require an LCD. So for example, I'm asked to evaluate the limit as x goes to 0 of the cosecant of x minus the cotangent. So I've just rewritten the question here. Now, off the top of my head, I don't know the cosecant of 0, which I'm going to plug in. So I'm going to go to that whole, let's rewrite everything in terms of sine and cosine. I do know cosecant is 1 over the sine, and cotangent is 1 over the tangent. But really, if tangent is sine over cosine, then cotangent is cosine over sine. So I'm taking the limit instead of this problem, same value, just a different way of looking at it. I've got the limit of 0, so I'm ready to go ahead and plug 0 in. I drop limit. I've evaluated this function at 0. 1 over the sine of 0 is really 1 over 0. Now 1 over 0 is undefined, but remember we're taking a limit, so it's not what actually happens at 1, it's what happens, 0. What happens close to 0. So at 0.00001, I'm going to get infinity. Cosine of 0 is 1. Sine of 0, just like it was a moment ago, is 0. So even though this would feel like it subtracts to 0, don't forget these terms are actually closer to infinity. And infinity, like minus infinity, may feel like it subtracts to 0, but this is of undeterminate form. So I'm qualified to rewrite it to get to use L'Hopital's. So what I want to do is take that rewritten form, but I need to get it down to a single fraction to really qualify for L'Hopital's. So I lucked out, and this problem already had like denominators, so I could just go ahead and subtract the numerators over that like denominator type. Still have the limit, because I was getting it down to a single function of L'Hopital form that's required. I'm now going to take the 0 to plug it in wherever x is. Cosine of 0 is 1, so I really just have 1 minus 1, which is 0, and sine of 0 is 0. I have indeterminate form. I'm allowed to use L'Hopital's. So I've copied the question. And now I'm ready to use L'Hopital's by indicating it with an x over h over my equal sign. The derivative of 1 is 0. The derivative of minus the cosine is minus negative the sine of x. And the derivative of the sine is the cosine. So really this just becomes positive. Again, if you know tangent, great. Otherwise, I'm going to plug 0 into both of these functions because I know sine of 0 is 0. Cosine of 0 is 1, and I have a limit of 0. The last type is indeterminate powers. We have some sort of exponent, a power to a base. So if you ever have 0 to the 0, infinity to the 0, or 1 to the infinity, which don't make sense in their natural form, that's what makes them indeterminate, then we can go ahead and use the method described below. 0 to the infinity almost feels like it should be one of the possible indeterminate powers, but it is not. Okay, so here's what we're going to do to solve these. You can see the problem we're going to work on down below. What we're going to do is we're going to label the equation as y. This allows us to have an actual equation, right? The function is y. So I'm going to be able to take the natural log of both sides. I'm going to use the laws of logs, the exponent part, to bring down in front. Then I'm going to evaluate from there using the above techniques, meaning L'Hopital's will probably come into play. And then I need to end the problem by raising it, both sides of my equation, to the power of e, and that will allow me to solve for y. Here we go. So I've got the limit as 0 goes the limit is x goes to 0 from the positive side of x to the power of square root of x. So if I plugged 0 in where x is and 0 in where the square root is, the square root of 0 is 0. So I really just have that whole 0 to 0, which is indeterminate power. So we're going to go ahead and take this equation and set it equal to 0. So what, I said 0, set it equal to y. So what we're saying is now we have an equation. We had a function, which is an expression, but I need to do some math to it, and having an equal sign will really help. So now, step 2 said take the natural log of both sides. So the natural log of y and the natural log of x to the power of square root of x. Now I'm going to use the law of logs so that this exponent can be brought down out front of my natural log. So I'm ready to take the limit of both sides. So I'm putting a limit in front of the left side. I'm putting a limit in front of the right side, right? I'm being fair and doing the same thing to both sides of the equation. Now, we're going to focus over here on the right side because really that's what we wanted to evaluate. So I first need to determine if I can even qualify for L'Hospital's. So I have the limit as x goes to 0 from the plus side, which now you understand why it was from the right side. So I plug 0 in for the square root of 0 to get 0. I plug 0 into the natural log, which tends towards negative infinity, and this satisfies product indeterminate. Remember, when it's product indeterminate, we want to take one of the functions, one of the terms, and write them in the denominator as a denominator. So we're not ready to use L'Hospital's yet. I'm just rewriting the question. I have the limit as x tends to 0 from the right, and I'm going to keep one of my functions as a numerator, and the other function I'm going to write as a denominator of the denominator. Let's double check that if I plug 0, limit's gone because I'm plugging 0 in, we know the natural log of 0 tends to negative infinity, and the square root of 0 is just 0. So this is really 1 over 0, which we said is essentially infinity because we're not actually using 0. We're using something super small close to it. I now have indeterminate form that qualifies for L'Hospital's. So I'm coming back to this original question. I'm using my L'Hospital notation. I'm leaving the limit the same, and the derivative of the natural log of x is 1 over x. Now, when I need to take the derivative of this denominator, I think it's better to think of it as a fractional exponent. The square root was 1/2, but it was in a denominator, so hopefully you can see that it was a negative. So I'm going to take this negative and put it out front in my derivative. I'm going to subtract denominator over denominator to get negative 3/2. And then I'm going to rewrite this to make a little bit more sense to me. I've got my 1 over x, and I'm going to, instead of divide, I'm going to multiply by the reciprocal. This would have been in the denominator, so the reciprocal brings this to the numerator. And my 1/2 kind of flips over, if you want to think of it that way. So cleaning this up, this was x to the 1. So I'm really subtracting 1, which is really like subtracting 2 over 2. So I'm going to end up with an exponent of positive 1/2. And this negative 2 is my coefficient, but I'm just left with over 1, and I don't need to write this over 1. So I have a limit of something I can go ahead and plug x into. Knowing that the 1/2 power is really the square root, I get 0. Okay, so where does all this tie back? We just said that the limit of the natural log of y is equal to this limit we worked on the right, but we found that that equals 0. So we're at our very last step, which says you want to end by raising both sides to a base of e. I'm raising both sides to base e. So I'm going to take this term and make it the exponent over e. I'm going to take this term and make it the exponent of e. Okay, So when you look at this left side of the question, because I have E and an ln, these can actually kind of be written interchangeably. It's the natural log of the limit of y. So when you see it that way, I'm able to use the exponential property that if you have e to a natural log power of something, it just equals that something. So my e to the natural log of something is just going to equal that something. On the right side, we had e to the 0, but remember e to the 0 is just 1. So if you can see this tie-in, I have the limit of y, but we said y is really this thing. So I really have the limit of x to the power of square root of x, and we just said that whole thing equals 1.